quantization and self-organizing map and adaptive resonance theory, that is VQ, SOM and ART. Now these three methods, that is your vector quantization and coherent self-organizing map and ART, these three methods are basically used for clustering the neurons, right, for grouping the neurons into a number of clusters. They're usually the two-layer artificial neural network. Only the input data are given, so these are unsupervised learning methods. They are self-organizing output. They will give you the output, and you have to check it whether it is the actual or not by some methods that we are going to tell, and in which cluster they will be, right. There are main two models are there, but before coming to SOM or ART, I just want to tell you that what do you mean by the vector quantization, because before artificial neural network, vector quantization we used to do for the clustering of the neurons, clustering of the any values, not neurons, any values. After the development of the neural network, we used to do this coherent SOM, which is near about based on this vector quantization, and ART is a completely different theory, right. So these are basically used for the clustering applications. Now before going to this vector quantization, I want to just tell you that what are the different clustering models. There are two types of clustering. One is known as your hard clustering, another is known as the soft clustering. But there are different types of models are there. One is your connectivity models. For example, the hierarchical clustering builds models based on the disconnectivity. That means where the connectivity is there, it will be in the one cluster. When there will be discontinuation, again the discontinuation of the link or connectivity, again it will be in the different cluster. Next, another model is your centroid model. If you have done k-means method or the k-means clustering method, you may have done in data mining. If you have read in data mining, then you have this classifier or the clustering models. For example, naive-based classifier or the k-means clustering method. The same method is used here in neural network also for the clustering, and these are basically depending on the centroid algorithm. Next is your distribution model. Clusters in this modeling, clusters are modeled using the statistical distribution, probabilistic distribution or some other statistical distribution, and normal distribution, Gaussian distribution. Like this, they carry out the different clusters. Density models. For the density models, we use the tools such as the dbScan and the optics. These are used for the clustering or the classification, right. dbScan is used in image processing also. If you want to do the the recognition of some mammograms or something else, so before doing the classification through the neural network, we can use this dbScan, which it can be used for the basic pre-processing classification. So dbScan can be used for the this density model classification. After that, there are subspace models, right. Subspace models in by clustering, that will be the two mode cluster. These are known as your two mode clusters. These are modeled with both cluster members and the relevant attributes also. Otherwise, group model is there if there is no clustering. That means some algorithm do not provide a refined model for their results, so you can just group it, right. That is a very basic methods of grouping or the clustering. And another is your graph based model, right. So let us start the vector quantization first. As I have told you, vector quantization doesn't come under the neural network models. Under neural network models, we have only the SOM method, that is coherent, and ART, and the different other methods for clustering, right. Nowadays, SVM classifier is also used for clustering or the classification. Now, vector quantization, it depends on the Euclidean distance. For example, here I have written that D is equal to XP minus CJ. What do you mean by the clustering? Clustering is a some neurons in one group. So first of all, for the to start with, what we do, for example, this is your first neuron. So this will be my center, right? This is known as your CJ, that will be the center, right? Now, with this center, that is your CJ, what we can do, that other neurons, whatever present, these are my XJ, for example, these are my XJ. Now what we do, each and every time we do the distance between the CJ and the XJ, we find the Euclidean distance. So here, that's why we have written the formula of Euclidean distance is, it has been represented as the double mod of xp minus cj, right? Double mod of xp minus cj means it is represented as like this, that is your xp minus cj. The formula for the Euclidean distance, it is written as square root of summation of, right? Summation means there are more than one neuron, so 1 to n neurons will be there. So xip minus cji, right? This whole square, right? This is whole square, and I belongs to 1 to n. That means if there are more than one neurons, then the Euclidean distance is your summation of xip, that means x1, x2, x3. These are my x1, x2, x3 different points, or the not neurons, different points, minus the center point, right? And whole square summation of that, and root of the whole summation. So this is known as your Euclidean distance. And in case of Cohen SOM also, we will find that we find out the Euclidean distance only. Depending on the Euclidean distance only, we do the clustering. So again, come to the slide. So what we are getting, that this is your actually the Euclidean distance. So what we have to find out, we have to find out that the minimum Euclidean distance from the from the cluster. This is your CJ is your jth cluster. Similarly, we have to find, for example, there are first time there will be one cluster only. After that, you just compare with the one cluster. After that, it may so happen that second cluster also have been formed. Now the points, whichever we have, the inputs, you have to compare the Euclidean distance of both the clusters. Now we have to find out the cluster which is giving you the minimum Euclidean distance. So this is the formula, that is your, we have to find out the k, where xp minus ck, that is your the Euclidean distance of x from the cluster k is less than xp minus cj. That means, or any other cluster, right? So for example, we have find out some cluster which is giving the minimum distance, right? Minimum distance, that means what, that there are more than 3 cluster, and this is my input, right? This is my x, and these are my c1, this is your c2, and this is your c3. Now we have to find out the Euclidean distance of x and c1. We have to find out the Euclidean distance of x and c2. Similarly, we have to find out the Euclidean distance of x and c3. For example, c2, x and c2 is giving the minimum Euclidean distance. So we have find out k is equal to, that means it will be 2. Right? So that's why we can find out that which cluster is giving you the minimum Euclidean distance, and that will be the cluster closer to the input, right? Which input we are checking out, that closer to this input. Now after we find out the minimum distance cluster or the minimum Euclidean distance cluster, then we have to test it with a threshold, right? We have to check it with a threshold, that if it is less than our threshold value, if it is greater than our threshold value. So depending on the value of the threshold, the cluster will be more accurate or the less accurate. That I will come to you, that how we can find out that it will be less accurate or the more accurate. That means if you take the cluster or the row as minimum, then there will be more clusters, because every time it will check with the threshold, and if it is less than threshold, then automatically it will be that cluster only that you have find out the minimum cluster. But if it is greater than threshold, then it will find out the new cluster. So this way the algorithm will go on, and every time the cluster, that is the center of the cluster, will be updated as 1 by n summation of x, but x belongs to Sn, that means the clusters belonging to the clusters, all x nahi hai, all the values of x we will take which are belongs to the same cluster. Then we can find out the center of the actual center, updated center size, and again the new center will be like this, and again we will find out the Euclidean distance. So this is depending on the Euclidean distance. It will be more clear if we take one example. So this is the example. There are 12 points, right? This is your 1, 2. There are 12 points. This is your 12th point, and in each and every point there is a x and y, right? Each and every point there is an x and y. Now, for example, we have to take rho, that is your threshold. Rho, that is threshold. For example, rho, let us take that it is 2. First of all, we are taking threshold distance equal to 2. Now, how to find out? Let us start with the first point, that is your 2 and 3. So, for the first pattern of 1, right? This is your pattern of 1 assigned to the cluster 1. That means first time it is your first cluster. This is your first cluster. There are no other points. So, first time there will be the origin of the cluster is your cluster 1, where the center is your 2 and 3. So, here the center is your cluster center is your 2 and 3, right? This is the cluster, that is your 2 and 3, and this is your assigned cluster is 1, and this is a pattern 1. Pattern 1 means this is your first pattern we are checking out, right? So, to start with, we are giving the same value as the first point. Now, come to the second. Second is your, that is your second pattern. It is giving the point 3 and 3. X values, the coordinate, it is giving the 3 and 3. Distance, to find out the distance, we want the two coordinates, x1, y1 and the x2, y2. Now, Euclidean distance, it says, as I have told you, that is your x1p minus cj1 whole square. X means it is a pixel point. That means it considers the x plus then another point, right? So, if we distance, to find out the distance between the 3 and 2, because our center point is your Cj is your 2 and 3, right? So, if we find out the distance, what will be the distance then, Euclidean distance? It will be root, it should be root, right? Summation, that means we will do the summation. Xi, our x is your 3, this is your our xi. Cji, that means first time Cji is your 2, right? So, that will be 3 minus 2 whole square. It will be whole square because I have given here, that is your xip minus cji whole square. Then after that we will do the summation. Then again the summation, then again 3 minus 3. So, this is our 3 and this is also our 3. So, it will be 3 minus 3 whole square. That means we are getting only 1. Right. So, in the second case, the Euclidean distance is 1. So, we have found out that Euclidean distance equal to 1. Right. Next condition, what is the condition? That after the finding the Euclidean distance, what we should do? We should test it with the threshold. In our case, threshold is equal to 2. Right? It is telling that if it is less than the threshold, that means distance is less than the threshold distance, then the pattern will be in the kth cluster only. That means whichever cluster we are comparing, right? Now we are comparing with the first cluster. This is your first cluster because we have only one cluster only. So we have found out the distance 1, and this 1 is less than the rho, that is your rho means that is equal to 2. So, it is less than 2, that means 1 is less than 2, that means this pattern belongs to the same cluster, that is your one cluster only. Clear? Now it is telling that after you find out that in which cluster it is, after that what you should do? You should find out the new cluster center, right? New cluster point. Now, what will be the new cluster point? It is the average 1 by n summation of x. Now, there will be 2 points definitely. Now what will be the point? Now here we had 2, here we have 3, right? 2 x point and 2 y point. So what will be the average? 2 plus 3 divided by 2. That means there are 2 points. So that will be divided by 2. That will be 2.5. And here that is 3 plus 3 divided by 2. That will be 3. So in the second case, what we are getting for pattern 2, it is assigned to class 1 because the distance between this and this, it will be 1, which is less than 2. That's why it is on the first cluster. And the cluster center, what will be? It will be the average 1 by nx divided summation of x. That will be 2.5 into n3. Right? These are my new points. Now for the cluster 1, we have the point is your 2.5 and 3.0. The before the 2 and 3, that was omitted. That has been updated, right? Now next is your pattern number 3. So let us take the pattern number 3. For pattern 3, the point is your 2 and 6. Till now also we have only one cluster. We have to check it that this 2 and 6 it will be containing in cluster 1 or it will be some new cluster, right? We have to find out. 2 and 6 are the point and the CJ is your 2.5 and 3, right? So what will be the distance? Again it will be root, right? It was 2 and 6, sorry. So it was 2 and 6, so distance will be 2 minus 2.5 because here it is a 2.5, 2 minus 2.5 whole square, right? Plus 6, it was 6, now here we have the 3, so 6 minus 3 whole square. So you will be getting 6 minus 3 is 3, 3 square root will be 3 only and here it will be 0.25, right? When you will add that 3.25 and you will, this will be 3 square. That means 9.25. When you will give the root, you will get the value 3.041381. Whatever you want to take, 3.04 also you can take or 3.041381 also you can take. So this is our distance. But now this distance will be checked with row. Our row is your 2. So it is greater than 2. That means it will not be in the same cluster. It will be the new cluster. So our new cluster, again I have named it, that is your cluster number 2. And for the cluster number 2, what will be the center? The center will be the same point as your x. Because it is a new cluster, you don't have to do the averaging, right? When it will be the same cluster, then only you will do the averaging of every point, right? Now we have only 2 and 6. That means we have the final point 2 and 6. Now for example, this is our 1 and 2. Now let us take the pattern 4. After that 5, 6 and 7 you do it yourself. I will just ask you. So pattern 4, again we are getting, what are the pattern 4? That is your 3 and 6. Now we have the 2 clusters, right? Cluster 1 point is your 2.5 and 3 and cluster 2 point is your 2 and 6. Now for the 2 cases, 2 cluster, we have to find out the distance, right? What will be the distance from the cluster 1? Let us find out the cluster 1, that is the point is your 3 and 6. Okay, then it will be root over of 3 minus 2.5 whole square, right? Plus 3 and 6, 6 minus 3 whole square, right? You will get some value here, right? And for the other case means from the point 2 and 6, what will be the distance? Again root over, here I am writing, or it is not visible. So if we are writing that root over, here we are writing that root over that is your 3 and 6, I suppose. So 3 minus 2 whole square plus 6 minus 6 whole square, right? That will be 0. That means 3 minus 2 whole square means that will be 1. And this 1 is definitely will be less than this, because here it is 6 minus 3 whole square, right? So whatever it will be less, that cluster we will take. So it will be containing in the cluster number 2 only, because the distance will be 1 and that distance it is 1 and it will be distance from the cluster 2. So that's why this will be belong to the cluster 2, because this is less than rho, that is your rho is your 2. So it will be then the same cluster from which the distance is less. So it will be then the same cluster. Now what will be the cluster center now? The cluster center will be this 2.6 and the average of 3.6, 3 and 6, 2 and 6 and 3 and 6. That means 3 plus 2 divided by 2, that will be 2.5, and 6 plus 6 divided by 2, that will be only 6. Now we are getting that is 2.5 and 6. Like this, we will be doing one by one, and all the points that will be in the 12 point we will do these 12 points, and we will find out that what are the clusters we can find out. If you have understood, you just do for me for 5, 6 and 7. Let us do for 5, 6 and 7, then it will be clear to you that whether you have understood or not and how to find out the cluster. Then we can match it, and after that I will go on further. So just you take 5 to 10 minutes and you carry on with the work of for 5, 6 and 7. That is a point 6, 3, 7, 3 and 6, 4. I'll ask the remote centers again after 10 minutes. You just do it yourself. If you find any difficulty anytime, you can just call, you can just talk to me. सबको on कर दो.
हेलो मैम, नेक्स्ट स्लाइड पे डाल दीजिएगा. हेलो, गुड मॉर्निंग मैत्री मैम. थैंक यू मैम.
Just 1 minute. Just 1 minute. This one, is it visible to you? Is this visible to you?
Yes, ma'am.
Okay. Just you write the point first. For the 5, that is 6, 3. For 6, it is 7, 3. And for 7, it is 6, 4. Right? These are the 3 points. And this also you will need. You just write down the points up to 7. After that, I will put it in the next slide. You have written? Okay, let me give you to the next slide. Now you do it.
Hello. Hello. Good morning, ma'am.
Good morning, Ji.
Ma'am, would you tell this cluster number 1 and cluster number 2? What are the points? Means from which we have to this
From cluster number 1, the point has come to 2.5 and 3. Just let me just remove this thing. Just 1 minute. So this is your slide. So for the cluster number 1, after the second pattern, we have got the cluster center as 2.5 and 3.
Okay. And for the second?
Right. And for the second, we have got after pattern 4, we have got the modified one, that is 2.5 and 6.
Okay.
Cluster center, modified one, right?
Okay.
And you have taken these values, that is 1 to 7 values that you have taken.
5, 6 and 7 I have taken.
5, 6, 7, 1, 2, 3, 4, 5 also you may require, but sorry, 1, 2, 3, 4. You may not require, but anyway, you can just note down these values also.
Yeah, I have noted down 5, 6 and 7. I will calculate.
Okay, okay.
Thank you.
Maybe pattern 5, yes. 6 and 3, and distance is your 3.5. समझ आ गई? 3.5 पैटर्न 2 के लिए है ना, क्लस्टर 2 के लिए हो गया ना ये क्लस्टर 2, और क्लस्टर 1 के लिए कितना था ये 2.5 एंड 3 था, तो भी तो माइनस करनी पड़ेगी ना, तो मिनिमम होगा वही लेना है। ये तो फर्स्ट क्लस्टर का फाइनली आ गया था 2.5 एंड 3, सेकंड क्लस्टर आफ्टर पैटर्न 4 आ गया था 2.5 एंड 6, ये आया था ना, ठीक है। अब जब आप फिफ्थ वाला नंबर कितना था 6 एंड 3, तो ये दोनों से माइनस करना पड़ेगा ना, दैट मींस 6 माइनस 3.5 होल स्क्वायर प्लस 3 माइनस 3 होल स्क्वायर, ठीक है। तो ये एक आ जाएगा कोई भी डिस्टेंस, फिर ये आ जाएगा 2.5, हाँ 6 माइनस 2.5 एंड 3 माइनस 6, तो दोनों में जो मिनिमम होगा वो लेना पड़ेगा, ठीक है। फिर मिनिमम होने के बावजूद भी देखना पड़ेगा कि इट इज ग्रेटर देन लो या लेस देन लो।
Hello. Hello. Hello, ma'am.
हेलो, यस,
Ma'am, the value of center same for all. Hello.
आप सिस्टम के सामने आई, आपका आवाज नहीं क्लियर है, अभी रिकॉर्डिंग में ऑफ कर देना फिर जब शुरू करोगी ना।
Hello.
हेलो, हाँ जी हाँ जी बताइए।
Ma'am, the centroid value of centroid is same for all. That is 2.5 and 3. Hello. Hello.
हेलो,
Ma'am, the value of centroid that is D is same for all.
पी,
The value of D that is centroid is same for all. That is 2.5.
हेलो
हेलो, हाँ जी, समझ नहीं आ रहा, आपका आवाज नहीं आ रही है।
Ma'am, the value of
जी मैम,
centroid.
वैल्यू ऑफ
हेलो
सेंट्रोइड आफ्टर फिफ्थ,
Yes, yes.
आफ्टर फिफ्थ मैम इट इज 4.25 एंड 3,
आफ्टर
हेलो
फिफ्थ, नो 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 नो, इट विल बी 6 एंड 3,
6 एंड 3,
yes,
हाउ इट इज
it will
मैम?
be it will be in the new cluster, cluster number 3,
क्लस्टर नंबर 3,
yes, it will be in the new cluster,
ओके
huh?
आवाज कहीं मर गई।
You have told the pattern 6 or pattern 5,
पैटर्न 5 मैम,
pattern 5, it will be the centroid will be 6 and 3, and it will be the it will belong to the new cluster that is equal to 3. Let me just do it.
इसका देखिए साउंड कम कर रखा है क्या वहाँ से भाई।
इसके रिकॉर्डिंग में डाल दो इसका, हरजो रिकॉर्डिंग।
हेलो
Yes,
मैम जब हम पैटर्न 4 का कर रहे हैं तो पैटर्न 4 से हम जो यूक्लिडियन डिस्टेंस है वो 3 और 2 के साथ कंपेयर करेंगे ना?
मैं जस्ट एक बार बता देती हूँ आपको। फिफ्थ पैटर्न के लिए the points are 6 and 3, that is your x coordinate and the y coordinate, right?
जी मैम।
So
Okay.
we have till now we have the two clusters we got. One is your C1, another is your C2, and this is my fifth point. I have to just check it that whether it is under C1 or it belongs to C2. Now in
Okay.
C1, after pattern 2, you can just check it. After pattern 2, the C1 has been modified to, I suppose, 2.5 and 3.
2.5 and 6.
Right? 2.5 and
Yes.
3.
Yes.
है ना? And in C2, after pattern 4, we have modified to 2.5 and 6.
Yes ma'am.
Right? Now we have to
Right.
find out the distance. Now how to find out the distance? Our point is 6 and 3. There will be two Euclidean distance. From C1, when we find out the Euclidean distance, what will be there? 6 minus 2.5 whole square plus 3 minus 3 whole square. That will be easier. 3.5 whole square. 3.5
Okay,
whole square, that will be equal to only 3.5. That will be the Euclidean distance of C1 and 5. Now we
Okay.
have to find out C2 and 5. Again, the C2 and 5 will be 6 minus 2.5 whole square plus 3 minus 6 whole square. That will be definitely, you can find out the value, that will be definitely will be greater than is your 3.5. That means the minimum Euclidean distance is 3.5, which is from C1. Right?
Okay.
That means minimum distance will be Euclidean distance for pattern 5 will be 3.5. But after that, we cannot just determine that it will belong to C1 only, because we have to check with row. Our threshold is equal to 2. So since this 3.5 is greater than 2, that means it will again clear it will prepare a new cluster for it, because it is greater than the threshold. So this 5 will belong to another cluster, that will be your C3. It will form a new cluster C3. Now when it will find out the C3, then finally what will be the cluster center of C3? Because till now we have got C1 equal to 2.5 and 3, C2 we have got 2.5 and 6. Now we have find out C3 with 5. Now in 5, what was the center? Since it is a new center, so it was x and y was 6 and 3. So for C3, the center coordinate will be 6 and 3, because it is into the new cluster. Have you understood that? Have you understood? Now you do it for the pattern 6. Pattern 6 and 7, I suppose now it will not be any problem. You just carry out for pattern 6. कौन सी clusters?
Hello, ma'am.
This
Hello. Cluster will
कौन
be
सी
3.
cluster से कम है?
Ma'am, cluster will be 3.
For pattern 6?
Yes, ma'am. Cluster will be
Yes.
3
Yes.
and center will be 6.5 and 3.
Very good. Perfectly all right. So for pattern 6, we are getting that it will belong to cluster 3 and the distance will be only 1 and the cluster center will be 6.5 and 3.
Yes,
Right?
ma'am.
And you do it for 7, because 7 में कुछ catch है.
7?
Then let us see.
For 7, cluster will be same 3
3, yes. Distance?
and distance will be 1.25. No, distance will be 1.11.
Very good. And what will be the cluster center?
Center will be 3.5. No. कितना होगा average? Ma'am, I haven't calculated yet.
आप कैलकुलेट करें.
कितना होगा average?
6.33.
It will be 6.5 and
Not
3.5.
6.5. No, not 6.5. It will be 6.33 because the cluster 3 final center you have got 6.5 and 3, right?
Yes, ma'am.
So you have to do the average of these two. For 7 we have got x coordinate is 6 and for cluster center we have got 6.5. So 6 plus 6.5,
Yeah.
that is your 12.5 whole square plus, right? 12.5 whole square, then it will be, 12.5 whole square, then it will be root. No.
6 plus 6.5 divided by 2.
Yes.
It will be 6.2. 6.2 and 3.5.
No. Just 1 minute. For pattern 7 you are doing, na?
Yes, ma'am.
It will be pattern 5 is your 5, 6, 7 are your just in 6, 12, the 19.
6.25. Average of 6.5 and 6 ka average.
No. You must have misunderstood the how it will find out the center. Center is basically, you can just note it here. Center, to find out the center, what we should do, that summation of x, right? It is giving the summation of x. That is your
Same में.
summation of x by n, right? Summation of x, it will not count the center. It will add the x point of those clusters which are in the same cluster. That means in our case 5, 6 and 7, these three are in the same cluster, right? So what will be the new center? New center is not the average of the center point. New center is your, that is 6 plus 7 plus 6.
So it is 6.33 and 3.33.
Yes, it should be 6.33 and 3.33. Absolutely right. Now I have got it. Now when we'll find out the pattern, we will check the distance between the centers, right? But when we'll find out the updated center, then it will be the plus of these 2 points, right? In previous also we have done like this only. You see, for after pattern 2, we have found out 2 plus 3 divided by 2, that is your 2.5, and 3 plus 3 divided by 2, that is your 3. So after pattern 2 C1 we have got 2.5 and 3, and since pattern 3 and 4 were into the cluster number 2, right? So in that case also, after pattern 4, when we have updated the center, we have done 2 plus 3 divided by 2, that is your 2.5, and 6 plus 6 divided by 2, that is your 6, right? That means 2.5 and 6. But in this case, when we will find out the updated center, so we have the 3 points. So we have to do the plus and then average. Similarly, for 6 plus 7 plus 6, that will be 6 plus 7 plus 6 divided by 3, and another will be 3 plus 4 divided by 3. That will be here, you will get 6.33, here you will get 3.33.
Hello.
Hello, yes ma'am?
Ma'am, we have just calculated the cluster for 6th point. So when we will calculate the for the point 7, so it will be the average for 5th and 6th point. when we are finding the center of the cluster, it would be 6 plus 7 divided by 2 and 3 plus 3 divided by 2. So why we are adding the 7th point? We have to still calculate for the 7th point.
No, no, we are calculating the center point of the 7 only for the next purpose. We have already calculated after pattern 6, we have already calculated the cluster center, that when we are telling that it is under the cluster number 3 and the new center will be your 6.5 and 3, that we have already calculated for cluster 6, sorry, pattern 6. Now when we are calculating for pattern 7, it is telling that for pattern 7, when we have found out that it is in the cluster number 3, the updated cluster center of pattern 7 we have to find out. That is cluster 3 after 7, right? So pattern.
Hello.
Yes.
Ma'am, to calculate it for the 7th point, we will just take the average of 5th and 6th point only. So why we are adding 7th point also to calculate the centroid cluster? That
because it is the current point. This is the current point. So after the current point also it should be included. What are the cluster point? It should be included again. Because you see, after we have done the pattern 2, after we have done what we have done, this is your cluster 1, that is your 1, and after pattern 2 we have found out that it also belongs to cluster 1. Then after that we have found out the new cluster center, and to find out the new cluster center after pattern 2, we have to add both these two, and we have to add both these two and the average. Similarly, for 3rd and 4, after pattern 4, we have done the 3 and 4 plus and this plus.
Yes.
After pattern 6, we have only 2 points. That's why we have done these 2 and these 2. Right? 6 and 7 by 2, that is your 13 by 2, that is your 6.5, and 3 plus 3 by 2, that is your 3. But when we are saying that 7th is also into the cluster 3, so we have now 3 points, this and this. So finally, when after 7 we have to find out, we have to do the average of these 3
points. Right. Thank you, ma'am. Clear.
Thank you. Okay. Any doubt from any center that how we have found out the cluster? Now, when we will do the each and every point, you will see this 3 cluster, that means C1, C2 and C3, and some points will be on the cluster 1, some points will be on the cluster 2, and some points will be on the cluster 3. Some points means maybe 1, 5, 6 and 7, whatever you have calculated, that will be in the cluster 1, cluster 2 and cluster 3. Now, what will be the effect of row? We have found out that because we cannot calculate all the values for all rows, so it has been shown that if row is greater, if row values is large, then the cluster point will be minimum. That means if row is your, for example, 4, then you may get the 2 clusters. That means the classification will not be accurate, clustering will not be accurate. If you give another more values, that means, for example, you are taking row is equal to, for example, 8, then you may get only 1 cluster only. That means all the points will be in the only 1 cluster. That means clustering is not accurate. So depending on the value of the threshold, the clusters will be, accurate. But definitely you should take the row value as an optimum value, so that there should not be any small cluster also, that is 1.1 cluster, 2.2 cluster. This should not be like this also, right? So this is about the vector quantization, and I am sure that you have understood it for clustering this. Now let us go for the another clustering, that is your Kohanen self-organizing map, right? So this comes under neural network. So Kohanen in 1984, he has developed this self-organizing map for clustering purpose only. But he also takes care of this Euclidean distance. Somewhat you will find out that there will be similarity, but here we will have the weight updation. Till now in vector quantization there was no weight was connected, because that was not, neuron was not taken into point. Now we will take the neurons or the layers, we will take into point. So there will be the input layer and the output layer fully connected, and there will be delta rule learning. That means something different we will find out in the weight updation. right? Weight updation will be with the help of the delta rule learning. So let us see that what will be there. You can find out here also that, let me just change the ink color. So you will find out that this is also the Euclidean delta W, and here we will find out the Euclidean distance only, that will come out. Only weights of the winning neuron and its neighbors are updated. 1 point. I will just explain that what you mean by this. Only weights of winning neuron and its neighbors are updated. That means if the winning neuron is 1 or some cluster or C1, that means only the neurons with that cluster which are connected with that cluster, only those neurons will be updated. Weights of winning neuron brought closer to the input pattern, right? From the diagram onwards, you can just see if we have can get the in self-organizing map. That means map means it will be somewhat, you know, that you should connect in a somewhat map. This is your map, right, within some area. Now in SOM, self-organizing map, we can have the hexagonal shape, or we can get the square shape, right? These two shapes we can get for the mapping of the neurons. Here in the example, I have shown the square mapping, right? Square shape. Now you can get, this is your actual neurons, and we have to come to the you know, the center neuron, right? We have to come to the center neuron, or we have to come to the closer to the input pattern. So one by one we will do. First of all, we will group. Again we will you know, reduce the radius. Again we will come to this one. Again we will reduce the radius depending on some calculation. Again we will come to this center, and finally we will again reduce the area, and for example you can come to the closer to this input. That way we come to the closer to the input pattern. Our aim is to bring the winning neuron to the closest pattern, that means closest cluster, right? Whatever may be cluster. That means if your cluster is C1, C2, C3 and C4, and if you have the input patterns, you have to check that all these input patterns belongs to which cluster, right? That was our aim. Now to find out, the training algorithm says that you have to set the learning rate and you have to set the weights. First of all, you have to initialize the weights, or you have to set the learning rate. Stopping condition. Some stopping condition we have to find out that what should be the stopping condition. If the stopping condition is true, then you have to just come out of the loop. If the stopping condition is false, that means you have to do the training again and again so that you can come to closer to this, right? Now each and every time you have to find out the Euclidean distance. That is same here we have done. That is your summation of, that is Wij minus Xi whole square. Squared Euclidean distance. That's why the root portion is not there. That is known as your compute squared Euclidean distance. Beforehand in vector quantization, what we have done? We have done the Euclidean distance, that considers the root of summation of something whole square. But here we have not got the root. That means it is a squared Euclidean distance. I is equal to 1 to n Wij minus Xi. This is your Xi. Wij minus Xi whole square. Right? You can write down. This is your Dj equal to I is equal to 1 to n. That is summation from all the neurons, Wij minus Xi whole square. Now again we have to find out the j for which the Dj is minimum, just like that what we have done in vector quantization. And finally we have to update the weight. That is different here, because in case of vector quantization we have not found out the any weight updation. Now what will be the weight updation? The Wij new will be Wij old plus it is finding the delta rule. As you must be remembering that what was the delta rule? That was alpha into, alpha is your learning rate, or C into, C was your learning rate. Xi minus Wij old, that was the difference, right? Xi, this should be I basically. Xi minus Wij old, and then alpha into this. So this will be the delta learning. That's why it is telling that it considers the delta learning rule, right? And after that, update the learning rate. If you want to update the learning rate, reduce the radius, that means area you should concentrate, and then uske baad, after that again you find out the test for the stopping condition, and finally you have to go to the loop. So this is all about your SOM training algorithm. Now let us do one example. Right? Let us do one example that you can just write down here. There are 5 clusters. If we do the examples, then it will be very clear to you. Right? If we have the 5 clusters, C1, C2, C3, C4 and C5, and U1 and U2, these are my 2 neurons, right? So these are the points, that is a point 2, point 3, 0.6, you bring to the slide, otherwise it will not be visible, I think. Right. So is it clear to you? You can just note down, that is U1 and U2, you just draw it, and there are 5 clusters, right? And the values are, I am just telling you, that is a 0.2, 0.3, this is 0.2, this is 0.3, then U1 and C2, that is your 0.6, 0.6, it is your 0.6, right? Then the U2 and C2, that is your 0.5. Then U1 and C3, the weight is your 0.4. This is your 0.4, right? Then U2 and C3, 0.7. U1 and C4, 0.4. This is again 0.4, then 0.6, then 0.2 and 0.8, right? And similar tabular form I have written, that is your 0.2 and 0.3 for the C1, 0.6 and 0.5 for C2, 0.4 and 0.7, this is for C3, 0.4 and 0.6 C4, and 0.2 and 0.8 for C5. And the input, it is telling that input vector is equal to 0.3 and 0.4. Sorry, this is 0.4, 0.4, and learning rate is equal to 0.3. So these are the 3 points we have got. Okay. Now let us calculate this one by one. Now what was the point? First of all, what should we find out? If you have the learning rate, what we should find out first? We have to find out the distance, right? Each and every distance we have to find out with this formula. That means D1, D2, D3, D4 and D5. 5 clusters with the input and the squared, right? Squared distance. One distance I will do for you. You can just check it and finally you calculate for others. This will be D1. What will be D1? It is not root, right? This like only the whole square and summation. Now our point is your 0.2 and input is your 0.3. That means it is your 0.2 minus 0.3 whole square plus next point is your 0.3. 0.3, that is your, this is weight, this is your 0.3, 0.3 minus our input is your 0.4. So 0.4 whole square. So this will be your D1. It is coming about 0.02. Similarly, you find D2, D3, D4 and D5. Because we have to find out the distance. This is your distance. So we have to find out according to Wij is your first term, Xi, that is your input in the second term. That's why we have given these weights, the cluster 1 weights, cluster 2 weights. So we have given the weights in the first term and the input, that is your 0.3 in the second term. You do it very quickly and you tell me that what is D2, D3, D4 and D5. उनको ऑन कर देना.
नहीं सुन रहा. Hello.
Yes, yes. What
The
is D2?
distances are, the D2 is 0.10.
Very good.
D3 is also 0.10.
Yes.
D4 is 0.05.
Something wrong is there. D4 should be 0.40 according to my calculation.
0.05, ma'am. All the candidates are getting the same value in my center.
0.05? Okay.
Yes, ma'am.
Okay.
And the
Then
last value
D5?
is 0.17.
This is 0.17.
Yes, ma'am.
Okay. Okay. Now, okay, fine. Other centers must have also got values only. So D1, D2, D3, D4, and D5. After we have found out this thing, what we have written in the algorithm, that we have written. Sorry. We have written that dj equal to this and find the index j for dj is minimum. So in our case dj is minimum, that is for the one case that will be 0.02. That means first cluster distance will be minimum, right? Now what is the next step? Next step is that you have to update the weight. Which weight? Only the C1 weight. You should not update C2, C3, C4 and C5. Only the cluster which is the minimum distance or it belongs to the cluster 1, only that weight you should update. Now what is the formula we have given? So let me just delete again. That is distance is your 0.02. Okay. So let me erase this. Okay. Now what will be the new distance? New distance Wij, right? It is telling Wij. I is your input, that is your only one input only we are taking, that is your 0.3 and 0.4, and j is also in your case is 1. J is also in your case is 1. J is the cluster name and I is your input neuron. In our case only one input neuron is there, so we are taking only W11. So what will be the W1 new? It is telling that W1 new will be W11 old. Right? What will be the weight plus it is telling that alpha into what is the formula? X minus Wij, X minus Wij old. That was the formula, right? Now if we take the value, what we are getting for the two values, that means for the first weight we are calculating. For the first weight, what was the old value? That was your 0.2, right? Plus for the first one, right? For the C1 there are two weights because neighboring weights we should change. So there are for the C1 there are two neighboring weights. One is a 0.2, another is a 0.3. The first point, that is a 0.2 plus alpha is your 0.3, right? And then x is your 0.3, that is your input, only one input, that is your 0.3, minus Wij old values is your again 0.2. So this will be your the actually the W11 new, right? So W11 new will be again with the formula I am again repeating. W11 old, that was old value is your 0.2 plus alpha we have taken as a learning rate as your 0.3 within bracket xi minus Wij. In our case xi is your 0.3, Wij old, that means old value is your 0.2. So this W11 new you will get as your 0.23. And similarly W21 new you will get as 0.33. So there will be two values, one will be W11 new and W21 new, right? That means what? For the next training purposes, again we will do the next one, right? For the next neuron, you can say this is only the one neuron. I have shown for the only one neuron. Now when you have got the updated weights, again you have to carry forward with the next neuron, right? You have to train to the next neuron. For the next neuron, what will be the weights? So here it will be 0.23, here it will be 0.33. right? Because new updated weight W11 is your 0.23 and W21 is your 0.33. So again you will get these values, and accordingly again for the next neuron you will calculate again DJ and accordingly which cluster it is, and finally you have to do the weight updation. So just like this you will get that all the neurons you can group it into the only different clusters which are available, right? These are the this is the way of self-organizing map, right? And new weights also we can calculate weight updation, and after that we can calculate for the, you know, if you get the second neuron, if you get the updation of C2, then again the weights connected with C2 it will change, again you will change the whole weight updation, again you will carry on for the third neuron. So similarly you can just group that all the neurons into the different clusters. So this is about the self-organizing map, and for all these you can write the MATLAB programming also depending on your steps, because all these algorithm is there. So to write a MATLAB programming is not a big issue. And it is very simple algorithm. So for each and every, you know, you can take, you know, just a set of 3 or 4 neurons, that means two values of all the neurons, and similarly you can take some weights, and how you can calculate this, write the algorithm according to your distance, and you can find out the minimum, then you can find out the old or updated weight, and after that it will belong to the cluster. Then finally you can give in cluster 1 these neurons are present, in cluster 2 these neurons are present, and in cluster 3 these neurons are present. So that will be your complete, you know, self-organizing map. And you can see for this clustering now no desired output or something is needed. You are just doing the unsupervised learning, no teacher, no desired output. You are just calculating and you are putting them into the clusters, right? Now, these are the some applications of SOM, that is your natural language processing, document clustering, document retrieval, automatic query, image segmentation, data mining, fuzzy partitioning, condition action association. So these are different types of SOM applications which are doing by the researchers in this category. Now the next one is your adaptive resonance theory, right? Now adaptive resonance theory, it says that it has been developed by Carpenter and the Grossberg in 1987, right? Now ART, there are main two types of ART, that is your adaptive resonance theory. One for ART1, another for is your ART2. Other ARTs also we are using with fuzzy, with map, all these things ART we are using. But ART1 basically for clustering the binary vectors, and ART2 is for the analog or continuous vector. Just like we have done in vector quantization the analog values, similarly we can do for ART2 is used for the analog or continuous values, and ART1 we use for the binary vectors. Now this is an online clustering algorithm. It is a recurrent type of network. We have already done recurrent type of network, and it is also the competitive output layer. Competition will be done in the output layer, that which cluster is the winning cluster, that cluster will take care of. Data clustering application, it has very specific problem, that is your stability and plasticity dilemma. It is very unique problem in case of ART, that is it should be stable and it should be plastic also. What do you mean by stable? Stable means a pattern should not oscillate among the different clusters. That means when you are clustering, it should not be the case that input pattern I1, it is first time it is coming into the cluster 1, and second time when you are updating again it is coming to the cluster 2, again when you are updating again it is coming to the cluster 3, because every time you will be doing the DJ and you will be finding that. But the distance, here it is not distance, here it is the different thing. So actually the pattern should not be like this, your neural network pattern, that the input already it will oscillate among the different clusters. That means your network should be very stable, it does not change the behavior. Plasticity, on the other hand, it says that if new pattern comes, right, it has the ability of the net, the net has the ability to respond to learn the new patterns, right? If you have the existing pattern, it will learn definitely, but after learning your network, when new pattern you are inputting, accordingly very accurately it should learn. That means it is plastic. That means general concept, plastic means what? That means you can extend it. Here also it says that it should be adaptive. That means it should have the plasticity. Any situation, any network environment, whatever behavior we change, automatically it should be adaptive and it should calculate. It should not stop. The network should not give that it cannot train the network, or it cannot, you know, validate the value, or it cannot test the value. The network should not give this one. It should be very plastic. Now these 2 points are in, you know, the in a different, just opposite word. One is, it is telling that it should be stable, that means it should not change. In another way it is telling that it should be, you know, adaptive. So that means whenever the new pattern we give, it should learn. That means these 2 ways is known as this is your stability plasticity dilemma. So this problem is very unique in ART. So when we design ART, when we you know, do the implementation in ART network with any weight updation or any values, we have to take care of these 2 points. One is your stability, another is your plasticity. Both these should have the optimal value. Then only you can design properly in case of the ART network. So these points is very important in case of the ART. So this is your you know, ART architecture. So in ART architecture we get the 2 you know, the layers, main layers. After that we will enter the another layer. This is one is your F1 layer, and this is your F2 layer. F1 layer is known as your input processing field. That is your where you are inputting, that is your F1. And in F2 these are the clusters, and F2 layer consists of the different types of clusters, and it has a mechanism to control the degree of similarity. That means definitely when you are inputting the pattern, it will say that it is depending on it belongs to cluster 1, or it belongs to cluster 2, or it belongs to cluster 3. So to find out the similarity, degree of similarity of patterns, we find out the vigilance test, and another is a reset mechanism. This is very important module in case of ART, different module. One is your vigilance test, another is your reset mechanism. And 2 types of weights are connected with this. One is your bottom up weight. Bottom up weight means B and IJ, right? I is your input, J is your cluster. And the top down weights, top down is your T, and it is represented as JI. That means it will come from cluster and it will come to the input, right? The representation we say like this. One is your BIJ from the bottom. When you are getting up, that means I is your neuron, J is your cluster. That's why we are giving BIJ. But when you are coming back top to bottom again, we are giving the top up, down the weights. So this will be TJI. That means J is your cluster and I is your input. And this F2 layer is a competitive layer. That means the competition of the cluster will be going on in F2, that the input neuron is belonging to cluster 1 or cluster 2 or cluster 3 or cluster 4. They will be doing the competition, and finally the winning cluster will give that I am the winner, and the weight updation will be according to my you know, my condition. So this is about the gist of the ART architecture. So here I have given just a diagram. This is in black color, so you must be understanding that. And anyway, I am just describing this. This is our new pattern. When the input is coming, this is our new pattern or the input. Here we do the categorization. What categorization? That is it the known cluster, or it is belonging to the any unknown cluster. That means whether it is belonging to the existing cluster, or it doesn't belong to any existing cluster, then you have to make the new cluster. So it is telling that categorization is it known, or is it unknown? And for doing this, you have to do these two process. One is your recognition, another is your comparison, right? First of all, you recognize, and after that you compare, and after that you determine that whether it is known, it belongs to known cluster or the unknown cluster. If it is a known cluster, then you give the winner node or the winner cluster, you adopt the winner cluster. And if it is an unknown cluster, then automatically you initialize that cluster again. That means node means initialize node means another cluster you will form, and that will be the new cluster. So that is only we have taken here, that incoming pattern will be matched with stored cluster templates, right? If it is same or if it is close to the stored cluster templates, then automatically the weights will be adapted to the matching cluster, and if not, the new cluster will be initiated with the pattern. So this is your ART algorithm. So ART1, as I have told, that is there are two main ARTs, ART1 and ART2. Besides this, we have the ART3 incorporates the chemical transmitters to control the search process in hierarchical ART structure, and also ART map, fuzzy ART map, DART, distributed ART or distributed ART map. So Gaussian ART map. So these are the different types of ARTs which are available in case of the neural network. Now this is your basic structure. As I have told you, this is your F1, as I have told. Let me just change the color again because it is your white diagram. So this is your F1 layer. I have divided, first of all, I have told there are two layers. One is your F1, another is your F2 layer, right? Now here I have divided the layers into two parts. One is your F1A, another is your F1B. So what I am telling, that F1A is your input layer. Definitely here we are giving the input, that is your S1 to Sn. These are my inputs. After that we are interfacing. That means we are converting into a layer which are known as your X1 to Xn. Namely, generally this Xi is your same as your Si. That means whatever input you are giving, that will be same in your Xi. But it may be different. Between them you can make any function, and Xi may be some changed version of input also. That also can be given. Now from Xn, this layer F1B, there is a connection to the F2 layer which is my competitive layer. And there is a connection you can see, that will be the upper connection also. This is your upper connection, and this is your top down connection, as I have told, that bottom up weights and the top down weights, both of them will be there. So what is the actually functionality of ART1? This is about the ART1 only, because the binary mode we are telling. So we are giving that this is your input pattern, right? That is S1 to Sn. After that it will go to the input layer. This input layer is generally what I have told, that is your F1B, that is your interface layer, right? After that it will go to the output layer. Output layer is your F2, that is your competitive layer, right? This is your F2 layer. And here output layer, the winning cluster will be determined with some method, that which cluster it is winner. That means this input pattern belongs to which cluster, that will be the winner cluster, right? If it is same, if it can be found out, how it will be checked that it is the same cluster or this input pattern belongs to this cluster. It checks with these weights, that is your bottom up weights, but it is not sufficient. What it does, that after finding the cluster, again it will give the the output to the input layer with the top down weights, and again here also again we have found out the output, and the whatever output we are getting there, it should be same as your input. Then only we will say that this cluster is the winning cluster. That means only one side communication we will not do. We will go to the cluster, again from cluster to the input. Again, if we have find out that both these two are the same, then only we can say that it is the winning cluster. Otherwise we can just change it. So this is about the reset module. Here I have given them, reset module is there. One is your reset, another is your grain control. I have told you there are 2 points we should take out. One is your vigilant test, another is your reset test, right? So reset module, they have the fixed connection weights. They implement the vigilance test, and excitatory connection from F1B and inhibitory connection from F1A. That means it is telling from the F1B, this is my F1B and this is my F1A. Excitatory connection from the F1B, that means here it will be plus, and the inhibitory connection from the F1A, that means here it will be minus. Similar case for the gain module also, excitatory connection from the input lines and inhibitory connection from the output layer. That means from the excitatory connection, that is output layer is your inhibitory, that means minus. From the input layer it will be plus, so that will be the excitatory connection, and this will be the inhibitory connection. There is a connections difference they are telling. So this is the algorithm, ART1 algorithm. Okay. Now let me start with the ART1 algorithm that we were at this point. So let me just elaborately say that what are the steps in ART1 algorithm. First of all, as we have seen earlier also, we have to initialize the parameter. So there are two parameters here. The scientist has given these two parameters. One is your L, another is your rho, another is your N. There are three parameters. So L should be greater than 1. What is L? L will be, it has been given by them that the bottom up approach will be, initiated or initial value of the bottom up approach will be L by L minus 1 plus N. That I will tell you. So this is the initialization of parameter. L must be greater than 1 and rho should be less than 1. Rho is your threshold. Now first of all, we have to initialize the weights also. There are two weights I have told. One is your Bij and another is your Tji. Now for the first time, Tji is equal to 1. That means all the T values, top down weights value, it will be 1. And Bij, that is equal to, that it is telling that that should be less than equal to L by L minus 1 plus N. So this is be less than L by L minus 1 plus N, and Tji equal to 1. That has been given by them only for the ART algorithm. Now it is saying that while stopping condition is false, that means when stopping condition is false, then you go for loop, right? Which loop? What do you want to do? It is telling that first of all you come to the initial position, that is your input. You have all the input vectors, as I have told you, that is your SI, all the input vectors. First of all you find the normalization of input, that is known as your norm of S. S means input. Norm of S means you do the summation of all S. Right? Norm of S means summation of all S. That means that is equal to summation of Si, whatever summation is there, right? And after that I have told that it will be finally, first of all there will be F1A, and after that it will be F1B. There are two layers, and I have told that F1B Xi generally it is same as your Si. So whatever Si we have got, that will be same as your in your Xi only. Now you go to F2. Now from F1, this is my F1, we are going to F2. Now which is the weight is connected with that? Bij. So it will be Bij will be connected with each and every weight. So what will be the Yj? Yj is your net, right? Yj will be the net. Now what will be the Yj? That will be the summation of Bij into Xi, right? Whatever Xi we have, since Si equal to Si, so Xi will be in the F1B layer, there will be X1, X2 or Xi. So Xi into Bij, and the summation of these two will be the final net, that is your Yj. Again it will be in the loop if the reset is true, right? If reset is false, then it will come out of the loop. Now we have to do the winning neuron or the winning cluster. We have so many clusters in the F2 layer. Now each and every for each and every cluster we have to find out the net, and finally we have to check that for what j this Yj is your minimum. Just like that we have pointed in vector quantization, we have done in SOM. Similarly we have to do in ART also. So the method is different. Here we are giving the output yj, we are finding out, and finally we are saying that for what j, this yj is your minimum. When we have found out the minimum j or minimum yj, that means that jth cluster is the winning cluster for us, right? Similar we have done in vector quantization also. Now here what is the difference? When we have found out the cluster, that is your Cj or what yj is your minimum value for this, in SOM or in case of vector quantization, it was the final step, right? When we have found out, so that cluster we have taken. But here they are telling again the second step you will do just for comparison purposes. This you have recognized, now you will do the comparison or the matching. Really it is for that or not. Now again what we will do, we will come down. We have reached here, right? Now we have reached here, now we are coming down. What we are doing, recomputation the activation of x for F1B. So we are doing TJI into SI, right? Whatever SI we have inputted, that should be, it will be coming down as TJI into SI. SI is your input. And finally we have to do this is your x, that means we are finding out again input and finding out the norm of x, that is your summation of the x. That means we have, first of all we had there, we have found pale SI. After that it has gone to the F1B layer where we are telling that xi is the same as your SI. So we are going up. Here we have found out the yj with the bij with xi and bij. We have found out the winning neuron or the winning cluster, and after that we are again coming down, and again we are finding xi again with this formula, that is xi is equal to si into tji, right? And when we have found out the xi, then this xi and the input si, that we are checking. If it is less than threshold, that means if it is your error controls is there, then you just omit this. And if it is greater than this, then you update. That means what is the update formula? That means update the weights. That is your bij equal to this and tji equal to this. This is the formula. According to the formula, whatever it will be done, then you can just calculate that what will be the bij and what will be the tji, and again the loop will go on. So this is your ART1 algorithm. There are two layers, input and the competitive layer. So if you want to find out, let me just tell you that what is the vigilance threshold, right? There is a term, that is your vigilance threshold. Vigilance threshold sets the granularity of clustering. That means how much big will be your cluster, how many neurons will be in one cluster. So that should be your main target of research. That is threshold. Which value of threshold you should take? It may be low, it may be high, it may be optimum. So for the low threshold, large mismatch accepted. But for the high threshold, small mismatch is accepted, right? Many small clusters, higher precision. Here it is a lesser precision. That means what? That if the row is large, then the cluster number will be, this is your large number of clusters. It is white in color, so it is not finding. Let me take the color red. Right? For the large row, what it will be the case? There will be a large number of clusters in there. For the small row, it is not precise. That means that there will be the, the cluster will be less. That means all the neurons will be tied to the one cluster only. That means the clustering will not be accurate. So if it is higher threshold, then the precision will be more. And if it is the low threshold, then precision will be less, right? So this is actually the vigilance threshold that you have to take care of. And this I have told you that after the, you find out that it is greater than x by s is greater than rho, then you have to adapt the weight or you have to change the weight. That I have given you already, the weight updation. Tji will be same as your xi only, and bij will be L into xi divided by L minus 1 plus the norm of x. This is your norm of x, that is a summation of x, right? This is your summation of x, this is the norm of x. So that will be the updated value of the bij, that is a bottom up approach. Now if I take one example that you can just write it down, then you can just do it. Just 1 minute. So let me write the problem first. Let me insert one blank slide. So let me insert the blank slide here. I will just write that the equation or the values, you can just note it down and you can just do it. So it says that consider the ART1 network with F1 layer and the F2 layer with the bottom up weights and the top down weights. So Bij, it is given as, so we are writing that Bij, it is a matrix, right? Half and 1 by 5, 1, 2, 3, 4, 5, 6, 7, 8, 9. Half, 0, half, 0, then half, and in this side all the values are 1 by 5. 8 values, 1, 2, 3, 4, 5, 6, 9 values, right? There are 9 values, that is your Bij. All are, these are 1 by 5, and this is half 0, half 0, half 0, like this. And the top down approach, it has been given as the matrix, that is your 1, 0, 1, 0, 1, 0, 1, 0, 1, and these are all ones. One zero one zero one zero 1, 0, 1, and all the values in the lower row, that will be equal to 1. And the input, what is the input pattern that I am giving you here? The input pattern, that is your SI, is given as 1 1 1 1, 0 1 1 1 1. There are 9 values. Vigilance parameter, that has been given as 0.4, right? First time it is the vigilance parameter, it is given as the 0.4. Now some values will be assigned to you, right? Some values I am giving you for the calculation. One value is your n, you need n equal to is your 9, right? Now L also you want, L is equal to is your 2, and rho, that is your vigilance parameter or threshold, vigilance threshold, that is equal to 0.4, right? M अभी नहीं चाहिए. So rho is equal to 0.4, n is equal to 1, and L is equal to 2. These are the 3 values. Now according to the your the algorithm, Now what you have to do, first of all, what you have to calculate, Bij, right? We have to first calculate, that is your S equal to summation of Si, right? And send input signal as into the F1A to F1B, that is Xi will be same as your Si, and after that you have to calculate Yj equal to Bij into Xi. Now we have Xi, we have the Bij. Bij is also given to us, right? Bij we don't have to now calculate. Finally, when we'll do the updated Bij, that time L or N will require. Now we have Bij and we have the Xi. So here you can find out the Yj, right? Bij into Xi, that will be your finally Yj. So for Yj, you can find out, first of all, first step is your summation of Si. That we have found out. Summation of Si. And what is your Si? Si is the input. This is your S. 1 plus 1 plus 1 plus 1, 4. Plus 1 plus 1 plus 1 plus 1. That means total Si is equal to 8. Is it so? This is your S. Second point, what it says, that Xi equal to Si. That means what will be your X? X also same as your Si, that is your 1 1 1 1 0 1 1 1 1. So this is your X. These two steps we have done already. So these are the two steps. One is your S, another is your X, right? These two steps we have done. And finally we have to do the Yj. This we have to calculate, Yj, right? You have the Bij and you have the Xi. So you can find out the Yj also, right? Both the terms are there with you. So you can find out the Yj. Now what will be your Yj? So Yj will be the matrix. So you have to find out Y1, Y2, Y3 and Y4. Similarly for Y8. For the 8 points, you have to calculate the, the Y matrix. After that, you have to find out that which one will be giving you the minimum value, and that will be the winning neuron, right? And after that, again, you come back to the initial part. Again, you calculate Tji. This is your Tji. Tji into Xi again. Then you have to match that whatever is your Si, that was your 8. And finally, you have to calculate what will be your X, and then this divided by this will be calculating as a less than rho or the greater than rho. And rho you have, that is your 0.4, and if it is greater than rho, then only you have to update. If it is less than rho, then you have to just omit it. So this is your ART1 algorithm, and you can write the MATLAB programming also for this ART1 algorithm. Right? For each and every clustering method you can write. K-means clustering also somewhere it is related to this. Naive-Bayes classifier also, that also somewhere related to this. All the classifiers or all the clustering methods are generally do the same algorithm only. Right? So these are the three clustering algorithms what we have done today. One is your vector quantization, another is your Cohen self-organizing map, and third one is your ART, that is your adaptive resonance theory.